Hello student, after seeing the kinematics part of uniform circular motion, let us see what is dynamics of uniform circular motion. Now in dynamics, we'll consider the force acting on the object while the object is moving on the circular track. Now we know once the object is moving on the circular track, it is subjected to centripetal acceleration, and the centripetal acceleration is equal to v square vr or omega square r. So let us see in different situations how this centripetal force is acting on the moving object on the circular track. Now in dynamics of circular motion, right? Now if the object is moving with constant speed, that is in uniform circular motion, the speed of the object is constant. Now we'll observe in uniform circular motion, the speed of the object remains constant, v, that remains constant. Now in this case, we'll observe, since the speed is constant, I can say everywhere it is subjected to a centripetal acceleration AC, that is equal to v square by r. So obviously, when a particle of mass m is moving, the centripetal force, or I can say the F centripetal force, or I can say it is central force also, central, that is equal to mass time acceleration towards the center, or centripetal acceleration. Now this value can be written as m v square by r is the centripetal force acting. Now whenever an object is moving on circular track, this much of force is required on the object to provide the acceleration v square by r, that is centripetal acceleration. Now if the object is not moving with constant speed, so let us take non-uniform circular motion. Now second case we'll take non-uniform, non-uniform circular motion. Now here the speed of the object may be function of time. Now in that situation, I'll get two acceleration. One is tangential acceleration, that is rate of change of speed dv by dt, and another is radial acceleration. Radial acceleration can be written as at any instant of time v square by r. So obviously the net acceleration can be written as root under a tangential square plus a radial square. Now a tangential is dv by dt whole square, and a radial can be written as v square by r whole square. Is it? This will be the net acceleration, a net. So obviously, in case of non-uniform circular motion, we need a force F net can be written as mass time acceleration, net acceleration, is it? And this can be m times root under dv by dt whole square, and then v square by r whole square. From this expression, we can find out the net force acting in case of non-uniform circular motion. So we'll see we need a centripetal force or central force while the object is traveling on the circular track. Now let us take different example of uniform circular motion. We'll see how the centripetal force is provided somewhere, friction force is acting somewhere. If we want to reduce the friction, the object, the backing of the road is done. So let us see different aspects of dynamics part. So first we'll see whenever we take a small mass attached to one end of the string, and the string is drilled in the horizontal circuit. In that case, how the centripetal force is provided on the object to take the object on the circular track. Now once the object is connected to one end of the string, we'll observe the tension acting in the string gives the necessary centripetal force acting on the object, on the mass, and the tension in the string will be equal to nothing but mass times centripetal acceleration, and mass times centripetal acceleration can be written as equal to mv square by r or m omega square, is it? So whenever the object is uh, moved in horizontal circuit with the help of a string, the tension developed in the string is mv square by r. Now in another example, while a cyclist is moving on the horizontal circular road, let us see bending of the cyclist. Now first example, I can take, first example we can write, suppose a string is there, a string, and a mass is attached and it is moved in the horizontal circle. Now here you will observe the tension acting in the string provides the necessary central force or centripetal force, that is mass times centripetal acceleration, and if it is moved with constant speed v, I can say it is equal to mv square by r. In case of where r is the length of the string, or I can say the circle in which the object is moving. So tension developed will be mv square by r. Now second example, let us take the bending of cyclist. Now whenever the cyclist is moving on the circular track, we'll observe on the circular track suppose this is normal, this is radius of the circular track, the center of the circular track, and this is normal. The cyclist has to bend in this direction, making theta angle with the vertical. Why? Once the cyclist is kept in the vertical direction, you will observe in that case normal reaction will balance mg. Now then there is nothing to provide the horizontal force or the force in the radial direction to provide the necessary centripetal force to the cyclist to move on the circular track. So once the cyclist bend his body, we will observe in reaction will come in this direction, or let us take or reaction R, I can say, and then the horizontal this will have two components. One will be in vertical direction, that is R cos theta, another will be in horizontal direction or towards the center, that is R sin theta. So I can say R sin theta is nothing but mass time the centripetal acceleration mc. The speed of the cyclist is v. I can say it is mv square by r. Let us take small r. Let us write down small r for the radius of the circle. Now r cos theta can be written as mg. So I can write down the tan theta is nothing but it is v square by gr. So the cyclist has to bend by theta angle from the normal to get a reaction in this direction, a reaction in the radial direction, and reaction in the vertical direction, that will balance the weight of the object. So tan theta is now you will observe from this expression, the more is the speed of the object, the more is the bending of the cyclist. If speed increases, the bending of the cyclist also increases. Now let us see in case of level circular road, third example, level circular road. What is level circular road? There is no banking on the circular track. Now both end of the circular track, I mean both the width of the circular track is at the same level. So in that case, suppose this is the circular track and object is here, right, and this is moving, this is mass m. Now on level circular road, what happens if the object is moving with certain constant speed v? You will observe here the centripetal acceleration is in this direction, AC, that is nothing but v square vr. Now some force should act on this in this direction to provide centripetal force. Now it is nothing but the frictional force acting here. We know the frictional force will act at the bottom of the object which is in contact with the ground, and this can I write F as frictional force. Now we know the frictional force is less or equal to mu s time, and so I can say the frictional force is going to provide which force? F centripetal or F central force, I can say the Fs is nothing but F centripetal will be less or equal to mu s time, and I can say this can be written as mv square by, let us take r is the radius here, mv square by should be less than mu s time, n is nothing but mg, so this gets cancelled. I can say the speed of the object will be less or equal to mu s g r, or I can say the maximum speed without skidding on this can be given to this object, that will be equal to root under mu s g r. This is the maximum speed of the object which can be given on the level circular track. Now sometimes what happens, if the object is small, no problem, some heavy load is going. Now when heavy load is going, in that case you will observe the mass, suppose a truck is loaded, a loaded truck is moving on this level circular track, what will happen? The mass is much more. In that case we will observe the frictional force which comes as frictional force, which is given as mu s time, normal reaction is mg. So we will observe as the mass of the object is increased, a frictional force is also increased, and a large frictional force is developed between the tire and the road, and in that situation the tire may get punctured or the tire may get damaged if the load on the vehicle is very large or mass is very large. So in that case, when the heavily loaded truck is moving on the circular track, if it is moving on level track and if it moves with large speed, then frictional force may damage the tire. So what we are going to do in that case, we provide banking, or banking of the road is done to reduce the frictional force acting between the tire and the road. Now in banking of the road, the outer edge of the circular track is raised in comparison to the inner edge. If we slightly raise the outer edge of the circular track, then we'll observe the normal reaction which was acting previously in level road in vertical direction will tilt, and the tilted normal reaction will provide some part of this tilted normal reaction will n sin theta will provide the centripetal force acting on the vehicle, and the vertical component of the normal reaction will balance the weight of the object. And once again we'll see the tan theta will come as just like bending of the cyclist, v square. So let us take what is banking of the road. Now it is clear that banking is done to reduce the frictional force acting between the tire and the heavily loaded truck. So let us see in banking how to find out the angle of inclination, how much banking is done, and how the speed is affected with the banking of circular track. Now banking of circular track. Banking. Let us take banking. Banking of Now in banking, what we are doing, suppose this is the outer edge of the road is raised slightly. If this is inner edge, let us take the outer edge is raised by h height. This is base B, width of the road. I can say this angle is theta. Now once the object is placed on this, or vehicle is moving on this one, what will happen? The normal reaction gets tilted from the vertical direction. Let us take, and this angle is theta. Then I can say, if you take this angle is theta, I can say in this direction you will observe n sine theta comes, and in vertical direction it is n cos theta, right? So I can find out the n sine theta provides the necessary centripetal force. N sine theta can be written as m v square by r, and n cos theta can be written as mg. So what banking is done, tan theta can be written as v square by gr. Is it? Tan theta, the angle of banking of the road, can be given as tan theta is v square. Now you will observe the more is, I can also write down tan theta is equals to, for small banking, tan theta can be written as sine theta, and this can be written as height by, let us take this b, and this can be written as v square by gr. So I can say the raising, this raised height is nothing but v square b by gr. This much height is raised. Now as the v is more, we will observe the height, the more banking is done, angle of banking is more in that situation. Now with banking, we are going to reduce the frictional force acting on the moving vehicle. So in that case, the tan theta can be written as v square by gr, and the frictional force is reduced to a large extent once we bank the road. So heavy vehicle can negotiate the circular track very easily, and negotiate the circular track with maximum speed. So this is all about. So then we'll see the conical pendulum, and then motion in vertical circle, that also we'll see. In conical pendulum, what happens? In conical pendulum is also example of uniform cell conical pendulum. We'll see, suppose with the help of a string, an object is hang here with mass m, and it is moved in horizontal circle. Mind it is moved in horizontal circle. Now this is the circle within this is moved, right? And let us see, the center of the circle is, this is point of suspension, POS, and this angle is, if this angle is theta, I can say here the tension in the string T can be written, this angle is theta, so I can say T cos theta, or T cos theta can be written as mg, and in this direction you will observe T sin theta can be written as m omega square r, where r is radius. So this is theta, and if L is the length of the string, I can say r will be equal to L sin theta, and h will be equal to L cos theta. So I can say from this m omega square r, I can say tan theta in nothing but omega square r by g. Is it? Now I can find out omega, nothing but it is g tan theta divided by This can be written. And then time period can be written as 2 pi by omega. Now I can write 2 pi, omega is nothing, but we will change g tan theta, and r can be written as L cos theta or r L cos theta. 2 pi, r can be written as L cos theta. We will observe sin theta by cos, or I can also say this can be replaced with sin theta also. I can say tan theta. Sin theta can be written as sin theta will be equal to this r divided by L. So r can be written as L sin theta naught. Is it L sin theta r? So if we place this value L sin theta, so I can say the time period will be equal to 2 pi root under L cos theta by g, L cos theta by g, and this is nothing but 2 pi root under h by g. So this way I can find out the angular velocity, the time period with which the bob is moving in horizontal circle. Now this simply you can remember, if the height of horizontal circle is h below the point of suspension, then the time period will be equal to 2 pi root under h by g, and omega can be written as 2 pi by omega. And this is the how the tension in the string will provide the one component will provide centripetal force, another component will balance the weight of the object. So this is all about conical pendulum. Now in next class we'll see the motion in verticals, a very interesting part. That is also example of non-uniform circular motion. Once the object is moving in vertical circuit, you will observe everywhere its speed is changing. So that is example of non-uniform circular motion. We'll see its dynamics part in the next class. Thank you. If you like this video, please do not forget to subscribe the channel. Thank you.